Okay, potentially the last video of this lecture module, and you're celebrating! Yay! Go take a trip to the beach after this and celebrate all of the stuff that you've learned about acid and base chemistry. I think that you'll be proud of yourself. So in this last lecture topic, we need to talk about buffers, folks. We need to figure out what a buffer is and how to handle one, and maybe even how to make one in general, with limited calculations and limited number of equations. That stuff doesn't belong in organic. We'll shove it out of the door. We'll say, Gen Chem, you take care of that. Analytical chemistry, if you're going to be a chemistry major, we'll see that buffer stuff again, come back. Quant class, well, quantitative analysis will bring in buffers one more time if it's a proper course. And that's when we can kind of address that situation again. But for here, just define it. Let's talk about it a little bit. Let's sit around the fire and chat and drink a nice little sip of coffee or something else, okay? All right, so when we talk about buffers, buffers are basically a solution. And this solution's purpose is to prevent a change in pH. That is the whole reason that we use a buffer. Bottom line, your blood is a buffer. Your blood has a buffer in it, and that buffer will prevent the change of pH of your blood. If your blood's pH changes like 0.2 to 0.3, then you could die. That's how important a buffer system is for you to live and breathe and to be happy every day. So buffers are going to be important. Buffers are also important in a laboratory. You know, one of my stories that I like to tell about buffers is that I worked for the University of Virginia's medical school. And we were doing research on frogs. And it was my job very early on, kind of a budding, just fresh graduate from a bachelor's degree program at the time. My job was to go into this lab and to help out the researchers who had PhDs that knew what they were doing, but they were removing frog eggs, and they were storing these frog eggs into a system. And this system was a solution of different reagents and chemicals and also a buffer. Well, one of my first jobs was to create a buffer system. And the buffer system required a little bit of acid, and it required a little bit of base, or really a salt that I would weigh out. And that's really where my bases were coming from. So I had to mix these two things together. I had to put them in solution. I had to make these fresh like every week or as often as needed for the researchers. No big deal. You know, I thought I was smart at the time. I knew that I could do the calculations, whatever. The problem here is that the acid, I was so accustomed to looking at molarity because that's what they taught me in undergraduate school was molarity. But then when I get into the real world and when I begin to start making these buffers, well, molarity was never mentioned. It was normality that was mentioned. And the normality, I really just thought it was the same as molarity. They were one letter off, so it was probably a misprint, right? I mean, they typed an N instead of an M, so I just made molarity acids, and before too long, all of the frog eggs began to die, and no one really knew why. This was something that they thought was the frog's problem. And they were extracting the frog eggs, and they were using my buffer solution that I was making, and I was making it from an acid and a base. And, you know, I knew that I was making it weighing out the right amount of solid. I mean, there's no way that I could mess that up. Then the acid part, I was making this acid, and I was making the normal like they thought, but I was really making molarity instead. So because I used a different concentration, I was killing all the frog eggs that they needed to do their research with. So, you know, That wasn't really the environment for me. That's not the reason that I left, but it was one of the very first early problems that I ran across and was introduced to in a working laboratory facility in research and development. I stayed there, a couple of years at least before I made the decision that I did not want to be stuck in a lab all day, every day. It was just not a working environment that I was very happy in. So I made the change over to teaching, and this is how you got me. So that was probably at this point in time, 17, 18 years ago, maybe even longer. And I've been teaching ever since. So with buffers, it is a acid and a base, but I need to put in here, it's a weak acid and a base, a corresponding base that matches it. So for instance, a weak acid would be CH3COOH. This is acetic. This was not one of those 6 or 7 strong acids that I told you that you should know, right? So this is a weak acid, and if that acid gave off its proton, well, its base would be this, CH3COO-. So this is the corresponding base that goes along with that weak acid. So I could make a buffer by mixing these two things together. And that's what that basically means. How much? Well, that really depends on how much I need to make. It depends on the strength of the buffer that I need. The strength of the buffer will basically be determinant on how long it could work. So the stronger that it is, the more it could neutralize and the better it could neutralize. But at the same time, I don't want to be wasteful. I don't want to overkill it. So there's always some calculations that go into making buffers. I've got to know how much of this to use and how much of this to use in order to ensure that we have enough buffer to satisfy the reaction that I'm doing. So this is an example of how I would make one. That's all that it is. It's a weak acid, and you remove the proton and you use that corresponding base. Well, this base will typically be regarded as a salt. I mean, I called it a salt up here. I'm going to call it a salt down here. And that salt is typically because they are always solids, and I weigh them out on a balance, and they are typically white crystalline in structure. Not all the times, but most of the time that they are. And most of the time, they're either sodium-based or potassium-based, one or the other. And the reason is because these things are cheap. Okay, they're very common. They are cheap. It doesn't break the bank for me to order these particular types of bases that we need to make these solutions with. So I would order potassium acetate, or I would order sodium acetate in order to make the solution for the base part. Also notice that when I did this here, the potassium and the sodium, these are metals. They are to the left of the periodic chart. Because they're to the left of that periodic chart, these are ionic compounds, which means that these are typically aqueous as far as solvent goes. So all of a sudden, we spent a whole lecture module talking about organics, talking about all of these, ionic versus covalent, what really isn't organic, and so forth. And now all of a sudden, I'm throwing ionics back into the picture. Yes, that's the way it is. And all of these acids that we've talked about too, I don't know if you've picked up on it or if you've realized it yet, but most of these acids are also aqueous. And that's because they are dissolved in water. So this whole lecture module, we have really focused on the aqueous polar type of chemistry that's really not related to organic. But the weird part about it is that it's many organic molecules that make that up. It's kind of weird and strange, isn't it? And it's due to polarity. It's due to acid base. It's due to the release of a proton, because at that point it gets fully charged. And when it becomes fully charged, these things can dissolve in water very easily. So this is a way I could take an organic molecule like acetic acid, and I could deprotonate it, and I could get a charge, and that charge now makes that molecule dissolve in water, with the simple removal of a hydrogen. And now you know why acid-base chemistry is so important in organic, because it changes the dynamic of the molecule if we begin to play around with these charges. So buffers, sometimes I'll have to make them in a lab. Again, the way that I make them is I'll choose a weak acid and its corresponding base. I'll weigh out a certain amount of the salt, and I'll measure out a certain amount of this acid, and I'll mix it together into a volumetric flask or something. I'll dilute up to the line, give it a good shake, give it a good mix, and now I have my buffer solution that I have just made. I can also control the pH of the buffer. So as you can imagine, the amount of acid that I use or the amount of base that I use will allow me to play around with the pHs. So if I want the pH to go up a little bit, maybe an 8 or a 9 and so forth, then I want to add more base to the pitcher, to the recipe. If I want the pH to be lower, maybe a 3 or a 4, then I want to add more acid to the recipe. Okay, it just matches the pH scale. That's all that it is. And in order for me to determine which is the proper weak acid to use, I need to look at pKa values. And I want to pick a weak acid that is plus or minus 1 as far as the buffer requirement. Okay, so what does that mean? Okay, this is starting to get jumbled up, I know. So just hold on a second. So this pKa value of acetic acid is 4.76, all right? So that means if I want a buffer, and that buffer needs a pH of, let's say, 9, because the reaction that I'm doing requires a solution of 9 as far as acidity goes, as far as pH goes. Well, acetic acid's not my best choice, because acetic acid would be really good for buffers that are plus or minus 1 from 4.76. So acetic acid would be good for a buffer that's like 3.6 to 5.6. And if I was working in a buffer range there, then acetic acid would be a pretty good acid for me to pick from. Okay, so I would get acetic, and then I would get the acetate, sodium acetate, potassium acetate, that base, and I would mix these two together. And depending on the ratio, how much acid and how much base I use, I could get this pH to change a little bit for me. So I could go to the more acidic side, or I could go to the more basic side, depending on how much of each one of these I use from up above. Well, pH buffer of 9, acetic acid's not going to be a very good one for that one, right? Because pH of 9 does not fit in this window. So I'm going to choose a different weak acid in order to do that. And I can pull up a PKA chart, right? I mean, we've talked about PKA charts at this point, and these PKA charts look something like this. And if I need a pH of a 9, I'm going to go somewhere that gives me a pH of a 9, give or take a little bit, give or take a 1. So if I look on the screen, look, HCN, well, there's an acid. That has a pKa of 9.4. So that's almost smack dab where I need to be. So there's a possible acid that I could use, but it might not be the only one. Down here at the bottom, I see ammonium chloride, NH4Cl. Well, that NH4Cl has a pKa of 9.23. I could use that one too if I wanted. And then here, BOH3. That has a pKa of 9.23. That's really close to 9. So I could use that acid as well. And there's just tons of different choices on here that I could pick from depending on what I have and what I would like to use. Okay, so this is the importance of a PKA chart yet again. Here we have an example. We have to make a buffer. I've got to pick out the right acid in order to make the buffer. The way that I pick out the proper acid, I pick one that is close to the pH that we need, plus or minus 1. That's a safe, fair bet or a choice to pick from. And there could be more than one correct answer, so you've got to be comfortable with that. And then when I pick that acid, I just use the corresponding base that goes along with it. So erase the hydrogen, and now you have the base that you need. In general chemistry, you talked about buffers. Buffer capacity was probably talked about. And again, if buffer capacity was not mentioned, I'm sorry. I hate it for you. I hate that you had that experience. But buffer capacity means that this buffer will get used up. So the buffers are not going to last forever. And this is the way a buffer will operate. I've got a buffer here, and in this buffer, I have a little bit of acid and I have a little bit of base. Okay? And it's all swimming around. I know it's there because I put it there. I measured out a little bit of weak acid, put it in solution. I measured out a little bit of the corresponding base. I put that in solution. So I know they're present. So what happens is that if you add something to this solution, and let's say that this is a base, that base will go in, and this extra acid will attack it and kill it out. So my buffer does not change. The pH does not change. The buffer prevents it. And then if I have a little bit of acid that gets added into this solution, that acid is added in, it would change the pH because I'm adding acid in, but this buffer has base, and that base will see that extra acid and it goes away again. And this dynamic continues to play. But there's going to be a certain point where I will add base or I will add acid, and there's no more of this in solution that can it out, right? So when we reach that point is called the capacity of the buffer. No longer can it do its job anymore. And if we add that extra acid or if we add that extra base, we will see a change, a dramatic change sometimes in the pH of the solution. And the reason is because we have added extra now. There's nothing in there that can cancel it out. So this is buffer capacity. And buffer capacity is related to the concentrations of the acid and the concentrations of the base that are present in that solution. So hopefully that was a review. Hopefully you talked about buffer capacity in general chemistry. Hopefully you talked about making a buffer in general chemistry. And on top of that, there is an equation, and it's called the HH equation. The HH equation stands for Henderson-Hasselbalch. All right, so Henderson-Hasselbalch equation looks like this. pH equals pKa plus log of my proton acceptor, which is a base, and my proton donor, which is my acid. A lot of times people would write it pH is equal to pKa plus log of my base over my acid. This is a shorthanded representation of calculating the pH of a buffer that I will make in a laboratory. So if I'm using acetic acid to make my buffer with, my acetic acid is 4.76. So that's the pKa that I am going to use. It's the pKa of the acid that I'm making the buffer with. And then this last piece of the equation, this plus log, this relates to that concentration that we were just talking about. You know, that concentration of acid and base play a role, and it can change the pH of that solution plus or minus 1 most of the time. So that's why this piece is included in the Henderson-Hasselbalch equation. So I'll calculate the concentration of the base that I've used in molarity. That's the problem. And that concentration might be 0.3. And then I calculate the concentration of the acid that I have used in molarity. And the concentration of that acid will go here to the bottom. Well, this will play a role in affecting the pH of the buffer. So I'll take log of 0.3 divided by 0.2. So that's 0.3 divided by 0.2 is 1.5. So log of 1.5 is 0.18. And 4.76 is the pKa of acetic acid. That's what I used to make the recipe with. So 4.76 plus 0.18 gives me 4.94. And this is the pH of that buffer that I have made if I use this much base and this much acid. That is the purpose of the HH equation. The other way that you could do this in the world of equilibria is to go back and do an ice chart. Oh, you're probably cringing. I know. I hate ice charts too. Initial, change, and equilibrium. If you didn't do ice chart in general chemistry in Chem 152, then you didn't take 152. That's all that class is supposed to be. All equilibria, acid-base equilibria, general equilibria, equilibria of solubility products. You should have spent probably 3 months on ice charts when you took that class. And if you did not, again, I'm sorry. But the ice chart was the first way that we could do or use to calculate these types of things. Well, no one wants to fool with ice chart unless they have to. And one of the ways around it is to use the Henderson-Hasselbalch equation. This is a shorthanded ice chart that we can use back in the day, especially for the world of acid and base, to calculate pH of these solutions. So what types of questions are you going to see from me? Well, the types of questions that you might see from me here are going to be the types of questions that would just basically give you the concentrations of the base and the acid. You just need to know where to plug them in. Okay, that's the only thing that I'm going to ask you to do. So in the question that you'll read, it will say, calculate the pH of the buffer if you have used this much acid and this much base. Okay, well, this equation I'm going to give you, I'm not going to require you to memorize this equation. So I'm going to give you pH equals pKa plus log of A minus over HA. I'm going to give you that. The only thing that you have to do is read the question, and when it says base, that's the number that you're going to plug in the top, and when it says acid, that's the number that you plug down here at the bottom. And then you clean up the equation and you solve for it. That's all that you'll have to do for these. I promise that's all that I'll ask. Again, I'm keeping it simple. I'm not treating this as a general chemistry class. I'm not treating this as a quantitative analysis class. This is organic. Buffers are part of organic, but the calculations are not. So it's important for us to get a general understanding of a buffer, how a buffer is made, what a buffer's purpose is, but I'm not necessarily going to focus on these types of equations in organic chemistry. That is for another class on a different date, on a different time. Okay? So there's your story with buffers. The other thing that I also want to mention while we're talking about charges and buffers and changing organic compounds into aqueous, they love to give you questions. And the questions are going to be, let's say that you take a separatory funnel. If you've never used a separatory funnel before, it's a piece of glassware. This is kind of crooked. I know I'm not the best artist. And this piece of glassware will hold a solution in it. It's called a separatory funnel because most of the time when we use these, we have two liquids, and those two liquids are not miscible. And miscible basically means that they don't mix. So I've got two different layers here, right? Layer 1 and layer 2 here at the bottom. One of these will typically be polar and the other one will be non-polar. It might not be this order every time though. So these two things can flip back and forth depending on what we use. It can flip back and forth. So sometimes the polar ones can be on the top and sometimes the polar solvent, it can be on the bottom. It just really depends on what we pull out and use for that particular lab. So this is called a separatory funnel. Two different layers of liquid in here. And there is a chance that I could take an organic molecule. And let's say that organic molecule is a solution that looks like CH3, CH2, CH2, CH3. This is a nonpolar molecule. And this nonpolar molecule, well, it's probably going to go into the nonpolar phase, right? So this is its natural tendency. But if this molecule had a PKA on it, there is a chance that I could play around with the pH of that solution and I could get this molecule charged. And if that molecule becomes charged, then all of a sudden I'll have a polar molecule. And just by changing the pH of the solution, that polar molecule now will be in the top layer and not in the bottom layer as expected. So there's going to be maybe some types of questions that you're going to get, and it's going to give you some organic compounds. And those organic compounds will have pKa's that are associated with them. And they're going to say, hey, you've got a pH here. This solution has a pH level. And you dump this organic into that pH solution. Well, you first are going to have to determine what it does. Is it neutral or is it charged? If it's neutral and the pH does not affect it at all, then it's probably going to go into the nonpolar layer. But if you put this organic compound in the pH and that pH forces it to spit off a hydrogen, and you get this positive piece or this negative piece, and sometimes this positive or negative forces that molecule into the polar layer instead of the nonpolar layer. So it's just a combination type of question. Again, don't let it trick you. It's just a wordy type of problem. They're trying to get you to think a little bit. They're trying to get you to apply the acid-base theory to these separations and what happens inside of solvents. Which layer does it go to? And all of that is driven because of its charge. That's what it is. What they like to use most of the time, they like to use ether and they like to use water. Sometimes they also like to use toluene. They will let you know which one's which most of the time. However, if this is the case, treat the ether and the toluene layer as the non-polar one. Even though ether is slightly polar, they're putting it in there because it's a really good organic solvent. So go ahead and treat it as non-polar. And then water, they are typically treating as the polar solvent almost every single time that they ask these questions. Okay, so the question again will be, here's an organic, here's its pKa. You put it in solution with a pH level of this. Which layer will it go to? Or, here are two organic compounds. Here's the pKa of the first one. Here's the pKa of the second one. How could you separate them using these two solvents? Well, to answer that question, you'll say, oh, well, the pKa of the first one, pKa of the second one, if I can get somewhere in the middle, right here, I can get one to get charged and one will stay neutral. Therefore, the charged one goes to the polar one and the neutral one goes to the nonpolar solvent. So once more, don't let those questions throw you off. They actually talk about this in your chapter. So if you're looking in your textbook and you're trying to follow along, this is typically included in the buffer section. So before the buffer or in the buffer section, in that general area of your chapter, they might even give you an example. And they love to show you an example of a separatory funnel during this as well. So as you flip through the book, page by page by page, if you see a picture of a separatory funnel, stop and then start reading around that area and you will see one or two of these example problems that they like to ask with this type of information. All right. Okay, so I think that we are over it. I think at this point we have talked about acids, we've talked about bases, We've talked about the purpose of PKA, how it affects the structure of an organic molecule, and now how it affects the solubility of the organic molecule as well. So I think this is enough general chemistry review. I mean, we've spent at least 2 weeks on this stuff now, right? At least, if you're taking it in the summer class. If you're taking it during a normal 16-week class, we have spent at least 3 to 4 weeks on this information because we have a little bit longer to cover material. So with that said, good luck in the lecture module. Good luck on the online assessments that you've done. And this will also finish up typically the first test information. And that first test information will focus on the first 2 lecture modules, which include review of general chemistry and review of general chemistry that we're going to call acid and base chemistry. All right. So good luck. If you have any questions at all, again, you know how to get a hold of me. Do not feel scared or timid to send me an email. That's why I'm here, right? I'm employed by Cape Fear to answer your questions. And if I did not enjoy answering your questions, if I did not want to answer your questions, then I probably should not be employed at Cape Fear doing the job that I'm doing. So never feel shy or backward about reaching out and contacting me, especially in organic, because folks, I'm going to be honest with you. I know that this is not easy for some of you, and that's okay. No one said that it had to be easy. No one said that you had to be perfect. But I'm going to make you better organic chemists by the time this semester is over. Just sit back and watch.